Hello, folks. I am Ayush, and today we discuss exponential families. We discuss mixture models, and we study a bit of probabilistic graphical models. So, today's lecture is not going to be as math heavy as we had in the last lecture, but I hope it will be interesting. So, let's get started. So, the first topic is exponential family. Now, when we talk about exponential families, we are talking about families of probability distributions, okay, which have some kind of exponential nature, and they have a specific structure, okay, and they have a parameter called as eta, which is called as a canonical or a natural parameter. And if we vary that parameter eta, we can get families of probability distributions. And these exponential families are so popular or so important is because they have some special properties. Like, for instance, when we'll discuss about the maximum entropy derivation, we will see that exponential families comes out as a result of maximizing the Lagrangian. So we will come to that, but let's go step by step. All right. So the first is exponential family. So this includes many common probability distributions which are parameterized by a parameter called as eta. Okay. We'll come to the natural form of it and how we write it down. So how we write it is, let us say that I consider a family of probability distributions, okay, which is parameterized by eta, okay, all right, and with fixed support over a d-dimensional vector. So my output y is basically a d-dimensional vector, all right. So with fixed support over this, and basically this is written in this form. So the distribution of the output y parameterized by eta can be written as 1 by z of eta exponential, and then you basically have eta transpose t of y. So we will define all these terms, all right? This z of eta, eta, and t of y, what these terms are, all right? We'll come to all of that. Okay. So what we can say is that if I basically write it in a simpler way, so this is clear, right? So we are considering a family of probability distributions with fixed support over yd, and this belongs to the exponential family if the density can be written in this particular form. All right. So this is in the exponential family if we can write the density in this particular form. So another way of writing it is some h of y. We'll come to that, what it is. Okay. Exponential eta transpose t of y minus a of eta. Okay. This h of y is a scaling constant, also called as the base measure. You have seen that when we write the Gaussian density, we always have a 1 by square root of 2 pi sigma square before the exponential, and that is there to ensure that the probability density function integrates to 1. All right, so this is that h of y. Okay, so h of y is called as the base measure. Okay, then another term is t of y. So this is the exponential family equation. All right, and actually we'll come to it, because the reason I am so much of interested in this exponential family is because distributions like, Gaussian, Bernoulli, binomial, categorical, these are actually, subsumed by the exponential family, or the exponential family subsumes those distributions. That is, those distributions are special cases. Like if we vary eta in different ways, we can get those distributions. So this is just like a very common, general thing that we are studying, right? And for special values of eta and sufficient statistics t of y, we can get these different, this probability distributions. Okay, so t of y is k dimensional, and this is called as the sufficient statistics. Sufficient statistics means that if I know, for instance, for a Gaussian, right? If I know the mean and the variance, all right, the sampled mean and the sampled variance, then I can get an idea of how the distribution will be. So I do not need those individual samples, right, to construct my distribution. That is why they are called as sufficient statistics. Okay, and eta are called as the natural or canonical parameters. All right, natural or canonical parameters. Okay, and z of eta that we wrote over here is actually called as the partition function, and a of eta. So if you take the a of eta inside exponential, what a of eta will be? Log z of eta, right? So this a of eta is called as the log partition function. And this log partition function is very interesting, because using the log partition function, we can actually get the we can generate the cumulants of a distribution that give us information about the distribution. We will come to this log partition function very soon. Okay, log partition function. And also we will come to this definition of a convex functions as well. And suffice it is to say right now is that we can also show, all right, that a is a convex function. That is, the log partition function is a convex function over the convex set psi. So if you do not know about convex functions now, no need to worry about it. You can just take the statement with a grain of salt, okay, for the time being. So that is eta, all eta, these particular etas such that a of eta is less than infinity. No need to worry about the statement, just focus on the equation. Okay, so now it is another point that we will come to is that, when we when we derive the Hessians of this log partition function, we will see that if it is positive definite, all right, then it's always good. But if it's positive semi-definite, then it can so happen, that we can have some ill kind of behavior. Now what do we mean by this ill kind of behavior? It basically means is that, you see, for every distribution, like let's say for Gaussian or Bernoulli, this eta should be uniquely identifiable, right? What do I mean by that is that, let's say if it is a binomial, then for that it should have some eta, all right? If it is Gaussian, then it should have some specific eta, right? It should not be that two different distributions have the same eta. So eta has to be uniquely identifiable. And for that, there is a condition, right? So how do we write it down? So you see that it is convenient to have natural parameters independent of each other. Okay? Just keep following me, you will understand eventually. Natural parameters independent of each other. So what do I mean by that? I mean to say is that it should be minimal. Minimal means what? It means basically that there should be no eta, which is some k dimensional, okay, excluding 0, such that eta transpose T of y is equal to 0. What does this statement says? So this statement is saying we should not have any non-zero eta that is linearly dependent. Okay, or this combination gives me 0, because if this becomes 0, then it does not become uniquely identifiable, right? We want unique identifiability. That is, we want this eta to specifically characterize, each specific distribution. It should not be that two different distributions give me the same eta. Then in that case, we'll not be able to make the division on the basis of eta, right? Okay, so got the idea? All right. So also, if we define, so now we are trying to make this equation more general. So if we define this eta as some function of phi, we can always have eta can be some function of some phi, all right, where phi is some other possibly smaller set of parameters, okay, then this function p of phi given y, because eta is now a function of phi, so I can write p of y given phi, and f is has parameters phi, all right? So p of y given phi, this equation becomes what? It is h of y, the scaling constant, okay, exponential of f phi transpose times sufficient statistics t of y minus a of eta, and eta is again f of phi, right? Okay, got it? Now if this transformation that we are going from phi to eta using eta equal to f of phi, okay, so if this is non-linear, or let's say is a non-linear transformation, then in that case, what do we call it as? In that case, we call it as a curved exponential family. In that case, we call it as a curved exponential family, all right? And if eta, which is some function of phi, becomes equal to phi, if eta equal to phi, in that case, what we call it is the canonical form, all right? We call it as the canonical form, okay, all right? And if t of y is equal to y, then it becomes, so, and then it becomes a natural exponential family, okay, natural exponential family, all right? So What does this equation becomes? The density of the distribution. What does it becomes? So my probability density, or my basically probability distribution, or the density, this becomes equal to h of y. Exponential means e to the power, okay, e raised to that. So eta is this, and t of y is same as y, all right, minus a of eta, all right. Now you will see that this equation, we can do very interesting things with that, with this equation. For instance, I will use this equation to show you that why for Bernoulli we are using that sigmoid function. All right, when we want to convert it to a probability distribution, why do we use a sigmoid function? It turns out that this comes from the exponential family, and exponential families are actually, they are basically, when I'll teach you all generalized linear models, we will see how these exponential families are used to derive the to get the basically the the parameters of various distributions, and you will see that it becomes so easy to compute the parameters of the distribution using the knowledge of exponential families. All right, okay. So let's take an example. All right. So what is the first example we can take? So we can take the case of our Bernoulli distribution. P of y given eta is equal to h of y exponential eta transpose t of y, eta transpose t of y minus a of eta. All right. Okay. So let's write it down. So for a Bernoulli distribution, all right, for a Bernoulli distribution, what was the equation for the probability density? So Bernoulli is concerned with whether I get a heads or a tails in my, what is the probability of getting a head in the next coin toss, or likewise a tail. All right. So Bernoulli of y, and of course it has some parameter mu, that is the probability of getting, let's say, heads in a coin toss. Okay. So mu to the power y, 1 minus mu to the power 1 minus y. So it's derived in the earlier lectures. We discussed it, why it is like that. So how can I write it? I can, so exp of log is that term, log 1 minus mu. Now I will show you two representations of this. One will be the non-minimal form, and another will be the minimal form, right? Okay. So how can I write it down? So you see, one very naive way is to think that, okay, how I can write it as exp of the sufficient statistics transpose eta, right? This form, all right. And my sufficient statistics becomes what? So you see, either it is y. So here y is binary valued, right? You should remember that y can only take 0 or 1. Mu can be between 0 and 1, but y will take either 0 or 1 because it's an outcome, either heads or tails, right? But this is a density, and mu is the mu is the parameter of it, like what is the probability of getting heads or tails, right? So t of y, so y can be 1 or y can be 0. So if it is 1, this value we are evaluating, right? So that is why you write it as an indicator function. All right. So don't overthink about this. Just remember that when y is 1, this term comes into play, right? So indicator function y equal to 1 is 1. So it's log mu. Otherwise, if y is 0, this term will vanish and we'll take this term, right? Just like how we have in the binary cross entropy loss, which we will study later on. Okay. And eta can be log mu and log 1 minus mu, right? So if I take this, I get this equation, right? But you see, here the problem is that, so first of all, mu is the mean parameter. All right, mu is my mean parameter. And here the problem is that if I take eta transpose t of y, what will I get? What will I get if I take, let us say that if eta I take it as 1, so what is 1 transpose t of y? It will be indicator function y is equal to 1 plus indicator function y is equal to 0 is equal to 1. So if I take eta as 1, then you see this eta transpose t of y became linearly dependent. And what was our condition? The condition was that eta transpose t of y should be equal to 0 only if eta is equal to 0, right? Otherwise, we have got a linear dependence of eta. That is, the parameters are dependent on each other, right? So eta will not be uniquely identifiable. All right. So in this case, what we call this as the overcomplete representation. Overcomplete because we are using extra parameters. We do not need that. We can come to even lesser number of parameters, okay? And for that we have the minimal representation. So this is the overcomplete representation, and we do not need this. So we will simplify it to the minimal, and then we will show how this sigmoid function comes in. That, you all just study that, okay, sigmoid function converts it to a probability distribution, but why? That we will answer. Okay, so what I can write is basically now the minimal representation. Okay, so to get the minimal representation, what we need to do is we need to again take this equation and revise it in a better way, right? And how we can do that? So exponential y, so log mu by 1 minus mu, I'm just taking this part, okay, plus log 1 minus mu, just simplified this expression. All right, so how I can write it? So this is analogous to, so sufficient statistics t of y transpose eta minus a of eta. So if I compare with this equation, what are the terms I get? So eta is equal to what? Log mu by 1 minus mu. Now remember that eta was my natural or the canonical parameter, right? And what is my sufficient statistics t of y? It is y. So I just compare, we just compare these two expressions. Okay? And then what is a of eta? Is minus log 1 minus mu. All right. So see, if I simplify the first expression, what will I get? So let us call it as 1, 2, and 3. So simplifying 1, if I take exponential on both sides, what do I get? E to the power eta is mu by 1 minus mu. So e to the power minus eta. All right. So mu is equal to 1 by 1 plus e to the power minus eta. Now look, isn't this the sigmoid? 1 by 1 plus e to the power minus w transpose x. So if eta is w transpose x, then do not I get the sigmoid function? And mu is exactly my prediction, the next toss being heads. So isn't this sigmoid? So you see how we have got the sigmoid function. So this is the beauty of this, exponential family, that it is a very general case. So this exponential family subsumes so many of these different beautiful distributions. It's as if we can have a bigger concrete model, and for that model the special cases are, these different distributions. Okay, so this is called as the mean parameter, and this eta is the canonical parameter. Canonical parameter. Now, I was saying about this log partition function, that it can generate, a different cumulants, like for instance, expectation of it, or the variance of it. So it can generate those cumulants of my distribution, right? So we come to that part now. All right. So log partition function log partition function is a cumulant generating function. Is a cumulant. Okay. Is a cumulant generating function. And the first cumulant of a distribution is its expectation or the expected value, and the second cumulant is the variance. Okay, the variance. All right. So what we can write is that the property that we wanted to mention is this: the derivatives of the log partition function of the log partition function can generate all the cumulants of a distribution. So isn't it beautiful that I do not need to store all the cumulants? I can just use the log partition function to generate all the cumulants. All right, can be used to generate all the cumulants of the sufficient statistics. Like the mean, okay, the variance. So the mean and the variance, these are what? For Gaussian, they will be the sufficient statistics. So it can generate all the cumulants of the sufficient statistics. For instance, if I take two cases, so gradient or the derivative of the so here I think, if you remember a bit of your calculus knowledge, that can help. We will cover some calculus part as well. So the gradient, or if you do not know about this del, just think that you are taking derivative, okay, of this basically log partition function. Okay, so this is equal to the expectation of the sufficient statistics. All right, and del square, that is the Hessian. If I take the second derivative of the log partition function, which is the Hessian, will be the covariance of my sufficient statistics, right? So this is just like the matrix. All right, and there's a property that states that, and this is what I wanted to mention, is that Hessian, this Hessian is positive definite. We have covered what positive definite means, right? It basically means that if I take some, let's say, vector z, then z transpose del square a of eta z, positive semi-definite actually. So this will be more than equal to zero. That is, for all, that is, this quadratic form will always be positive, more than equal to zero. All right. So if the Hessian is positive definite, then we will prove that, so Hessian if the Hessian now this Hessian is basically positive definite, and we'll prove that this actually implies that the log partition function is convex in eta. Now, why are we so interested in this log partition function being convex in eta? There is a reason behind it, students or folks. Why this convex in eta? I am so much of interested in this. The reason being that if you take the log of this function, all right, the log, see, I need convexity or concavity because I want my distribution to be well behaved. That is, it should have only one minima or a global minima or a global maxima, right? Because either I maximize or minimize, I do something of that sort, right? To come to that optimal point, or whatever, like for the well behaved case or for the loss functions we want, like, so you get my point. We want to maximize the log likelihood. And if we have many minimas, then when we are doing this gradient descent, when we will do, which I'll teach you all later on, but gradient descent, I think I gave some intuition as well, that we take the step of the opposite to the highest ascent. All right, so if we have many minimas, we might get stuck in a local minima rather than finding the true global minima or the true global maxima. All right, so if I take the log of this, what do I get is eta transpose T of y minus A of eta. Now see, one thing I wanted to show you is that, you see, this eta transpose T of y, this is linear, right? So this part is both convex and concave. But if A of eta is convex, then this entire thing will become concave. If it is neither convex or concave, then we run into a problem, right? But if it is convex, then the minus of this would mean concave. And if this log function is concave, it mean it will be something bending upwards like this. So if it is concave, it will be something like this. So we'll get a unique global maxima. So when we do the gradient descent or the gradient ascent, we will actually reach to the highest log likelihood point, which is what I wanted to do, right? In machine learning, I want to maximize my log likelihood. What we can say is that, what I can write is basically implies A of eta is convex in eta. All right. So in that case, if A of eta is convex in eta, then this, the log likelihood that we are, so much concerned about, this log likelihood. So what it will have is, so basically the maximum likelihood estimate will have a global maxima. All right. Now let me write down the definition of convex function. Okay. Convex function. Okay. So f of x is convex if the line segment joining any two points lies above the graph. So I'll give you the visual how it is. For instance, what it is saying is that a function fx is convex if the line segment joining any two point lies above the graph. So it's very simple, right? For instance, if I consider, let's say, this kind of a plot, this is my graph, okay, and let's say this is my x-axis, okay. So let us say this is some point x1 and this is some point x2, and this is the line segment joining x1 and x2. So what we are saying is that, uh, any 2 points on this segment should be above this graph. And how do we mathematically write it? Okay, this is a very beautiful way to write it down. So for x1 comma x2, okay, belonging basically x1 x2 and some lambda. Why do I need lambda? Because I have to traverse the line segment. So how can I traverse it? So I can take, let's say, x1. All right, I can take x1 lambda times x1 plus 1 minus lambda times x2. And if I vary the lambda, you see, if lambda is equal to 1, then I am at x1. If lambda equal to 0, I am at x2. And in any values in between, lambda between 0 and 1, I will be in this line, right? So if I take the function of this point, that is, I am traversing along this part of the graph. So what does it says? That this line segment should be above this curve. That is, this graph should be below this segment. So how can I write it down? So let us say, how do I take any some point? That is lambda x1, all right, plus 1 minus lambda, this is the point x2, right, some point. And basically for the segment, how do I basically get that? So you see, this is what, this is f of x1, right? And this is what, f of x2. So if I traverse along this segment, then I will take what, lambda times f of x1 plus 1 minus lambda times f of x2. So here, so you see, this point is always above this point, this point is always above this point. So that is why we wrote this equation. So that is what the convex function is. Okay, it's just like a bowl opening upward, and concave is just opposite. It's just like a bowl going down. All right, and that is why we need convex, because you see, these convex functions are well behaved. All right, and basically, yeah, okay. So you got the idea, right, of this convex functions. All right, you got the idea for this part. Okay. So we now cover some of these points that I mentioned, because I have to give proofs, because we made some statements like, if the why the first of all, why is the covariance matrix positive semi-definite, right? And then we will come to realize is that why does a positive uh, definite Hessian means that it is convex. So let's write down some proofs. Okay, so the first part is, why is covariance matrix, why is covariance matrix positive semi-definite? That is, what we are trying to say is that for some vector v transpose covariance of yv is more than equal to 0. Okay, so we will do it with the some rules of variance that we basically derived earlier. But how we can write is that, so let's say I take some, now I have my sufficient statistics, right, t of y. So y is random, so t of y will be random, right? So for any random vector t of y and a non-zero vector v, okay, so v is my v, all right. So what I can write is that z, which is scalar, okay, I can write it in, I can write some z as v transpose t of y, right? So we always know that the variance cannot be negative, because variance was expectation of y minus mu whole squared, and the quantities inside the square are real. So variance is always positive. So we have discussed it in the previous lectures. So what is the variance of z? This is variance of this. Now I have derived that if I take variance of, let's say, a sigma, let's say. So what do we get it? We get it as a sigma a transpose, right? So let's say v transpose is a, then what do I get? I get v transpose covariance of the sufficient statistics. So variance of not this a sigma, but let's say some a x. So where, let's say, covariance of x is, let's say, sigma. All right, then this is what we had, right? So this is what we get, and this is non-negative, right? So this is more than equal to 0, right, for all v. So this is the definition of a positive semi-definite matrix, that this condition is more than equal to 0. And remember, I was saying about that unique identifiability, right? That eta transpose t of y should be equal to 0 only for eta equal to 0 case. It turns out that if this more than equal to, if this is positive definite, meaning this equal to sign is not there, then in that case you see that the covariance is, kind of positive definite. Okay, all right, so the covariance matrix would be positive definite, and in that case we have that well defined case that eta will be uniquely identifiable. Okay, so just a kind of connection we had. So it is the definition of PSD matrix, and it is strictly positive definite rather than just semi-definite, as long as the number of components or eta transpose t of y is equal to 0 holds only for eta equal to 0. All right, just follow that properly. Okay, now also you see, as del square of a eta, the Hessian of the log partition function was equal to the covariance of sufficient statistics, which we mentioned as the second point earlier slide if you look. So v transpose del square a eta, v should also be more than equal to 0 from this equation and using this fact, right? So what I can say is that a of eta is positive semi-definite. All right. Now the next point is that why does del square a eta, okay, is positive semi-definite? So why does a positive semi-definite Hessian, because we have to prove, right? We said that if the Hessian is positive semi-definite, it will be convex. The function a of eta will be convex. Why is it so? Why is that a of eta is convex if del square of a eta is positive semi-definite? So we come to that proof. Okay, so why does a positive semi-definite Hessian imply convexity? We will use Taylor series expansion for this. Okay, and basically here we have the second order condition for convexity. So if you recall, if I write the Taylor's theorem in this case, then what I can say is that, so for any 2 points, say eta 1 and eta 2, we expand the Taylor series around eta 1. If I do that, I can write the the log partition function for eta 2 as an expansion around eta 1. Okay, so that is a of eta 1 plus gradient a of eta 1 transpose eta minus eta 1. All right, so it is basically eta 2 actually, and transpose del square a zeta eta 2 minus eta 1, plus you will have some higher order terms that we can ignore. Okay, so higher order terms, I'm ignoring that, and this part, basically del square of a eta, what I can write it is that, so I'm making an approximation, right, a second order approximation, and this zeta is basically on the line segment between eta 1 and eta 2. So you can think it this way: between eta 1 and eta 2, on the line segment we have the zeta. Okay, so zeta is the line segment between eta 1 and eta 2. And what did I say? I said that del square of a eta is positive semi-definite, meaning v transpose del square a eta v is more than equal to 0. So this eta 2 minus eta 1 is like some v that I can take, right? So as del, as this as del square of a zeta is positive semi-definite, it means that this term is positive. So a of eta 2 is more than equal to a of eta 1 plus gradient a of eta 1 transpose eta 2 minus eta 1. Now this is actually the case of convexity. Why? First order case of convexity. Why? Visually, if I show you, see, what did I say? That the line segment should always be above the graph. So think this way. If I draw a graph like this, think this way, very simple way. If I have some graph like this, okay, so let us say that this is my, so it's like a bowl moving up, right? Let us say this is eta 1. So what is this point? A of eta 1. This is a convex function, all right? And you see, if I take some point eta 2, then the tangent line, this tangent line will always be below the graph because this is opening up, right? Are you getting it? This is opening up. Okay, so this is basically what? This is a of eta 2 here. Now what is this height? This height is basically equal to what? Nothing but the height by base is the tan theta, which is the tangent. So this height is del of a eta 1 transpose eta 2 minus eta 1, because the slope of the tangent I am considering at eta 1, that is why the tangent I am taking at eta 1, right? And this is above this height. Okay, got the idea? So that is why this is the convex function. So if it is a positive semi-definite Hessian, it will imply convexity, all right? And this is the first order condition characterization of convexity, all right? But anyways, this orders you don't have to mug up, you just understand the visuals. Okay, just understand the visuals of it properly. Okay, and the beauty is that if it's convex, then we will have a unique global maxima or minima, unique global minima for the convex case. Okay, so a of eta is convex in eta, all right? Okay, next we discuss a bit of directional derivatives. Okay, so directional derivatives is will be like a supplementary topic, you can say, but I am covering it because you will need it like extensively later on. I could have skipped it, but I think directional derivatives can help you in understanding the concepts. Okay, directional derivatives, we will have when we take the derivative, like let's say a function mapping from a vector to a scalar. Okay, in that case, if I take the derivative of that function, since it is it's mapped from a multiple variables to a single variable. All right, so we have to understand multivariable change of rule. Okay, and directional derivatives basically means what? That we are defining derivatives of a multivariate function for multivariate function defined in a particular direction. Here we consider the direction along a straight line path. Okay, because if we take a curve, if we take the direction along some curve, if we traverse, then the equations become a little bit more complex. So for simplicity, we move along some direction but in a straight path. Okay, so along a straight line path, along a straight line path. So say that I there is some x, there is some initial point, let's say x, and I traverse along the direction v. All right, so basically t is some real, x and v are vectors, and z is also a vector, right? So at t equal to 0, z of 0 is at x. All right, and as we increase the value of t, we move along the direction of v. Okay, so as t increases, all right, z of t slides along v. Z of t slides along v. Okay, so let us define some function g of t as, because remember a we were taking the log partition function. Okay, and z is a vector, right? And it is parameterized by t, because as t increases, z changes and moves along v. So x and v are like constants because v is just a direction, x is the starting point, so it is parameterized by t. So z is a function of t. Okay, so a of z of t, so you can think of this as the log partition function. I'm just trying to give the context, I'm trying to give the context. Okay, this is the log partition function. So z is a vector, right? So zi of t is basically what? xi plus t of vi. All right, and I can be 1 to n. Let's say if the vectors are n dimensional. Okay, so z of t is equal to z1t, z2t, znt. All right, this is my vector. Okay, now this function g of t is basically what? So it is a function of z of t. So we have what? A of z1t, z2t, zn of t. All right, if I take the derivative of uh, zit, of course I'll take it with respect to t because it's a parameter of t. Then what do I get? I get v of I. All right, and if I take a double derivative, it is 0. Clear? For all I between 1 to n. Now the multivariate chain rule, what does it state? So the multivariate chain rule if I have to write it down, you tell me what is the derivative of g dash of t. How can I write the derivative? See, first I take the derivative of the log partition function with respect to all zi's. Okay, and then with and then zi with respect to t for all zi's. What is the logic? That since a is a function of all z's, so if I wiggle my t, each of the individual z's will change, right? And then I have to define the partial derivative of a with respect to the zi's as well, and those zi's are also affected by t. Okay, so just write like an intuitive explanation. What I can write it is that, you see, if z1 is, let's say, wiggled alone, so by dz1, then what is the change of a? How do I define that? So we get dou a by dou z1, okay, into dz1, right? Oh, all right. And actually this should be dz1 by dt, because um, then it's only changing, all right, because here we have a g dash, so this is the derivative with respect to t. So we take the partial derivative of a with respect to zi's, and then dzi dt. So if I wiggle z1 only by dz1, then what is the change that I get for what is the change that I get in a? Dou a by dou z1 into dz1. Likewise, if I wiggle z2, then what do I get? Dou a by dou z2 into dz2, right? And so on and so forth. And then we have to define, and then we are taking the derivative of g with respect to t, right? So we'll have with respect to dt, all right? That is, if all the coordinates move, because t moves, so all the coordinates move, right? So I'm just writing it down, and I think this makes sense intuitively, right? You measure the change with respect to each zi's, and then zi with respect to t, all right? So what do I get? So g dash of t is equal to, so dou a z of t dou zi into dzi dt, which is what? Vi, all right? Zi dash, right? This is zi dash, which is vi, all right? Clear? Now you see, how can I write this summation? If I had to write this summation, how can I write it? Okay, so you see, this gradient of the log partition function is what? The log partition is a scalar, right? You should keep this in mind, that a is just mapping from Rn to R, right? Because this log partition function is scalar, right? And we're taking the gradient, we are taking the derivative of it, the gradient of this basically. So dou z2, all right, dou az, dou zn, and basically what is my v? So v is again a vector, right? So if I take the inner product, I get this summation, right? So g dash of t is equal to az transpose v. Okay, this equation is clear. Okay, now we come to the second derivative. Okay, now if I again take a derivative of g double dash t, what am I evaluating basically? So again I'm taking a derivative with respect to t of this whole term. Now see, vi was just a direction, right? So vi is a constant when I take the derivative with respect to t. Okay, so what I actually need to compute is this term, right? So d dt dou a z of t dou z of I. Now look, here again we should have something like this summation coming into picture, right? And why should this summation come into picture? The reason being that, you see, that firstly, these a as z1 z2 zn, these are not linearly separable, right? So when I take the partial derivative of a with respect to z1, let's say, I can get some z2 z3 terms, right? So when I take the derivative with respect to t, I have to take into account again the same way that the partial derivative of this with respect to each of the zi's, and then how that zi is changing with respect to dt, right? Because if I change t, then all the zi's will, if I wiggle t, then all the zi's will wiggle, and all those zi's wiggling will wiggle the a. All right, got the idea? So what I can write, so what we get is this thing will be equal to, so what I can write down is g double dash t is basically equal to, or if I just write this term first, because, so since I have already used I, so I will use some another j for the sum, right? Just like I did the dow zi, now we do dow zj, all right? Dow a of zt into dow zi, right? Into dzj dt. And what is dzj dt? Vj, very simple. So dow 2 a zt, dow zj, dow zi, and this is same as dow zi, dow zj, right? Because of the symmetry of this Hessian or the covariance stuff, right? So there is symmetry. So dow zj, dow zi will be same as if I write I here or j here, okay? And this is vj. So what does this become? So this is, let's say, 1, and this is, let's say, 2, okay? So from 1 and 2, from 1 and 2, what I can say is that g double dash t, the double derivative is to n, j is equal to 1 to n, vi dow to azt, dow zi, dow zj into vj. All right, we can write this. Now if I define this term, this, okay, so if we define, I hope this is clear to you. If we define this term, or let's say the h of z as dow square az, and that we can do by element wise defining. So we ensure that each element of the Hessian matches with this dow square a, all right? Dow zi, dow zj. In that case, what do we get? So if I write this v transpose h of z of v, what will I get? I'll get, so first we have the with vi. If I just multiply this two, what do I get? The summation here. So h of z, h of z, ij into vj. And if I just expand it, what do I get? So if you just, like, kind of expand it, you will get the terms. Vi summation j equal to 1 to n dow to az, dow zi, dow zj, vj. And this is the same as this. Now you will say vi is outside. You can take vi inside as well, because vi is because it is anyways inside the I summation. So even if I take it inside the j summation, it will be the same, right? So they are same. Okay, so the second derivative of this function g, or the Hessian of the log partition function, will be equal to V transpose del square A z of t into V. All right. This is the second derivative. So I think more important than mugging up these facts is to understand how we derived it, right? The idea that we used. That is more important, okay? Now coming back to the maximum entropy family that we studied, the exponential family equation. Let's keep this for reference. Now what we prove is the maximum entropy derivation of the exponential family. Of the exponential family. Okay. And first of all, what does this term maximum entropy mean? I'm writing that down. So, among all distributions satisfying the facts we know, we choose one that assumes least amount of information. Least extra information, okay. And or you can say least extra assumptions, you can say least number of assumptions. And what do we mean by least number of assumptions? So first of all, the idea is that we have some facts given, like how the distribution will be. For instance, let's say I know the empirical mean and the empirical variance, all right? So given those empirical mean and empirical variance, what should be the distribution that I should choose? Because when I'm choosing a distribution, I am inherently making an assumption, all right, that it will look somewhat like this or something in some way. I should make sure that I introduce least number of bias, right? Because my bias should not be very high, right? Because let's say if I was given, let's say, empirical mean and empirical variance, what distribution can I fit so that I do not add any of my bias? I should only use the information given to me by the data. So that is called as the maximum entropy derivation. That if I try to maximize the entropy given the assumptions, we will come to an exponential family form. Very interesting fact. All right. What does least number of assumptions mean? Or bias? So here what we are saying is that we search for a distribution So did you get the idea, intuitively? Like, intuitively you got the idea, right? That I'm given my empirical mean and empirical variance. Now I need to find some distribution to fit it, right? But I should not include, like for instance, we know that we fit the uniform distribution. That brings in least number of assumption. But that is for a specific case, right? But if we are given the empirical mean and empirical variance, what distribution should I fit? That is the important question, right? Because when we are fitting a distribution, we are bringing in some kind of bias. Okay, because we are choosing a distribution and we are just given the empirical mean and the empirical variance. So I should introduce that distribution that adds least number of bias. For instance, let's say if I have some data about something, so when I make a conclusion, I'll try to make sure that I do not bring in much of my own bias, right? I will try to infer from what the data is given to me. So that is what we are trying to do, or that is what we'll do, right? Least number of assumptions means that we search for a distribution that is as close as possible to our prior q of x. Now, what should we take our prior as? A uniform distribution, right? Because uniform distribution means it does not make any kind of assumption. It assumes uniformity everywhere, right? So we'll come to this, like when I take qx proportional to 1 or a uniform, we'll get this exponential family form, which is so beautiful to appreciate, I mean, it's really so beautiful. So to our prior q of x, okay, in the sense that, in the sense of KL divergence. So KL divergence, we will discuss this when we study information theory. What KL divergence means between two distributions means we want to see how similar two distributions are. The KL divergence will try to assess how similar are two distributions. If they are very dissimilar, the KL value will be very high. If they are if they are almost similar, then the KL value is very close to zero. All right. So in the sense of KL divergence, and of course we will have some constraints, right? Because when we write the expectations and the probability distributions, they sum to 1. So those constraints also have to be satisfied, right? So while satisfying our constraints, okay, so mathematically what we write is, I want to find some p of x, because that is what is unknown, right? I want to find a density p of x, the distribution, to describe some data. And what have I been given? Given the expected values. And expected values are always found, like we do the empirical sampling, right? And that we use it as an expectation, proxy for expectation, right? So given the expected values, so these are known of functions fx, right? So what is the first equation that I have? So integral. So basically, how do we write expectation? Fx px dx is equal to fk of x, right? This is the expectation, or simply capital Fk, because it is not a function of x. The expected values do not depend on the x, right? So they are just constants. So this is the integral, okay? And our prior belief is in some distribution q of x, and if we want to take least number of assumptions, our prior belief should be uniform distribution, okay? So what we are saying is, we want to find this distribution, some p, such that I minimize my KL divergence, okay? Subject to constraints. Subject to constraints. That is, first is, so see, if we use a uniform prior, because we want to make least number of assumptions, right? So if we use a uniform prior, q of x is proportional to 1, right? Now when you write the dkl, I'll later on say that dkl is p log p by q. All right, so argmin p log p minus, so you can just write it as functions of x, okay? And if you're finding that kl value, all right, or just think this way, okay? So arg minimum now tell me log qx is constant, so what do I get? And this is basically a summation over x, right? So you have summation over all possible x's for the kl, and this is p of x log some constant c. So you see log c comes out, summation p of x comes in, summation of p of x is what? 1. Density sum up to 1. So this is argmin is same as minus of argmax of this p of x log p of x. Now this term we call it as entropy. We will study in information theory in more detail. So argmax of entropy. And my constraints, so this is just some, I'm doing some manipulation, but just focus on this main equation, right? And basically another of my, so this is my first constraint, c1. What are the other constraints? Densities are always non-negative, okay? And another constraint is that probabilities sum to 1. Now if I want to minimize or maximize subject to constraint, and if I want to convert this constraint problem to an unconstrained problem, we use something called as Lagrangian, okay? So using Lagrangian to convert constrained to unconstrained problem. That is my Lagrangian. So you see, I will maximize my Lagrangian, so I will minimize my KL divergence, right? So minimizing the KL divergence means maximizing the negative of KL divergence. And we have the Lagrangian constraints. The constraints make sure that they are satisfied. For instance, you have some first is that this should sum to 1. All right, so these are the constraint forms basically. Lambda k, so summation k lambda k f of k, okay, minus summation x p of x f k x. All right, so these constraints that I have written, they are there. Why? Because this should sum to 1. So when we come to the optimal point by differentiating it and taking the derivatives and making the first order derivative 0, these terms will become 0, right? The lambda k and lambda naughts will take those signs in that respective way. All right, okay. So when we take the derivatives, so treating p as a fixed length vector, if I take the partial derivatives, so dow j dow pc is equal to, so I take the derivative of these terms. So first I take the derivative of this, what do I get? So I am taking element wise, okay? So I am taking derivatives element wise. P of c means p of x equal to c, right? So when the x takes value c, then I take. So first I take of this. So what do I get? I'll get it as minus log p of x equal to c by q of x equal to c. First we take this derivative, then we can take this one. So minus p of x equal to c into 1 by p of x equal to c into q of x equal to c into 1 by q of x equal to c, all right, minus lambda naught plus minus lambda k, or lambda x equal to c, right, or summation k, yeah, okay. So lambda k, because there's again a summation inside, so we take at p of x equal to c, so we get f of k x, basically f of k x equal to c, all right, and this we equate it to 0. So in very simple terms, what do I get? I get p of x equal to c by q of x equal to c minus 1 minus lambda naught, okay, minus summation k lambda k f k x equal to c, all right, and this is equal to 0. So if I take 1 plus lambda naught as some constant, okay, and if I take out the logs, what do I get? P of x equal to c is equal to q of x equal to c, all right, by z into e to the power minus summation k lambda k f k x equal to c. So this was for element wise. So for each element, if I do, I can write it down. So let me write it down clearly. What do I get? So I basically get this thing, right? So what do I get? So I can write it down as p of x equal to q of x by z, and then x power e of minus summation k lambda k f k x, where z is equal to e to the power 1 plus lambda naught. Okay. So you get the stuff, right? This is what we get. And this thing, the normalization constant will be just sum the densities to 1, right? So what do I get? This is of exponential family form. If you see, I can always equate these terms, right? Z can come up and it can become a of eta as log of z, log z eta, right? So this has a form of exponential family. So we proved that if we are given some expected values and if we make least number of assumptions, we get the derivation for exponential family in the exponential form, because q of x will be identity in that case, right? Q of x will be proportional to 1. So p of x becomes this form, lambda k f k x, all right. So it becomes in the form of an exponential family, all right. Okay. So this exactly has the form of exponential family, and f of x that I have over here, okay, this is the vector of sufficient statistics, and minus lambda are the natural parameters. Why? Because eta transpose is there, so we have minus lambda if we compare these two. All right. And say as an example, if f1x was x and f2x was x square, that is, these were my functions, and if I get some try to get some expected values out of that, and then if I solve this, then by matching the first and the second moments we get a Gaussian distribution. Okay, matching the first and second moments, we get a Gaussian distribution. Okay, so mixture models, mixture models are basically mixture of multiple models, as the name suggests, and we can use these mixture models to approximate any kind of complex distribution if the number of latents or the number of mixtures taken is large. Simply put, mixture models are very expressive. Okay, so we study a Gaussian mixture model, and before that let's first study mixture models. Okay, so the title is mixture models. Okay, so this mixture models helps us to create complex probability model. Because if we take mixtures of them, we can approximate, let's say, any kind of mixed Gaussians or whatever you say. Okay, so here what we do is we take convex combinations of simple distribution. So convex combinations of simple distributions, and that is p of y given theta. So I consider all mixture components. Now see, what is the logic? Each mix to construct, let's say, some p of y given theta, that is some distribution, I will try to assign probabilities, because we can take, let's say, if I have capital K mixtures, okay, then each mixture has some probability, some prior probability of being picked up. Okay, so that is given by some pi k times. Now once we pick up that mixture which has some probability, because it's a hierarchical approach, right? With some probability I choose one mixture, and then once I've chosen like I choose one model from that mixture, and once I've chosen that specific basically simple model, then I will try to see what is the probability of that, basically the density of that specific model inside the mixture, right? So pi of k for choosing the kth mixture, and the probability of the distribution of that mixture component, right? The prior probability of that mixture component times the probability density of that mixture component, okay, the distribution of that, and a convex combination summed over all of this. That means summation pi k will also be 1, right? So summation, because it's a convex combination, right? So pi k will sum to 1. So p of k is called as the kth mixture component. This is my kth mixture component, and pi k are the mixture weights. Okay, and pi of k of course is non-negative and should be between 0 and 1. All right. So as I said that we consider it as a hierarchical approach of first selecting that mixture component with some probability, and then the distribution of that mixture component itself. All right. So this is nothing but a hierarchical way of model, right? So how can I associate the number of mixture components, right? That can be some kind of latent, right? Because let's say if I have 5 mixture components, then I can think of this as 5 latent components. All right. So what I can write down is that my hierarchical model, so it's a first we have the discrete latent variables, okay, for the mixture components that we have. All right. So Z. So let's say that I have capital K mixture components. So Z can take any value between 1 and capital K. So this is basically which distribution to use to generate Y. So you see each distribution has some kind of weightage to it, right? That is given by pi k. That is how strong that basically mixture component is. And then we are taking a combination of that. Okay. So now this latent, that we have taken, this P of Z, this is should have some kind of prior, right? Because when I say that Z can take any values between 1 and capital K, it means what? It means that choosing each mixture component has some probability of being selected. So this reminds us of what? A categorical distribution. Let us say we have 3 mixture components. Mixture 1 has a probability of, let's say, 0.2 of being picked up. Mixture 2 has, let's say, 0.3. Mixture 3 has, let's say, 0.5. Right? So what this thing, the act of selecting that mixture component is itself a categorical distribution, correct? It is a categorical distribution. Got the point? So we have to assume some prior on the latent. So what is the probability that the latent takes some value k, right? So that is pi k. That is the probability, right? Okay. So what I can write now, the conditional, that is, once I have selected that latent, the kth latent, once I have selected that, then I am dealing with that specific distribution, the kth component distribution, which is nothing but pky, all right, which is p of y given theta k. And what is this then? So this part, for some small kth, it is pi of small k, right? So we can say that this p of z given theta is nothing but categorical distribution, right? So Z follows a categorical distribution because this is a categorical. For the kth component, it's pi k. For the one, it is pi 1, right? So you remember our earlier lectures, right? So the joint model, my joint model can be written as first of all, what are the parameters of my model? So the theta parameters are what? The priors that I can have on the latents, and also the, once I choose the mixture component, let's say pi 1, it will have its own set of parameters. Let us say that is theta 1, and so on and so forth, right? So P of y given theta, all right, this can be written as pi k, which is again P of z equal to k into theta. Just we are marginalizing, right? So we are taking convex combination, or you can say we are marginalizing out the latent, right? And this equation intuitively also makes sense, correct? It makes sense, all right? Okay, so this we have written, all right. So P of y given theta is basically summation small k equal to 1 to capital K pi k into P of y given theta k. So this is clear? Okay. So now that we have this basic form, you see, when the individual mixture components are Gaussian, that is P of y given theta k is Gaussian, in that case, it becomes a Gaussian mixture model, right? As simple as that, nothing complicated. So Gaussian mixture models. So what we can say is that, or the mixture of Gaussians, so P of y given theta will be the prior probability of picking a Gaussian component times. So once I have picked up a Gaussian component, the Gaussian will have its own mean and covariance parameterized by k, because we are talking about the small kth component, and we sum over all capital K components. So see, this is capital K, right? And this is the small kth component, right? So the small k is ranging from 1 to capital K. All right, keep these things in mind. Okay. So as the number of mixtures grows large, mixture components grows large, we can approximate any smooth distribution. Okay, so we can approximate any smooth distribution over d dimensions, capital D RD dimensions. Okay, so basically when I'm learning this, you see this model, this is an unconditional model, right? We are learning the density. So in a way, because we are learning the density, we are doing what? We are learning unsupervised, because it is not conditional. I mean, it is, you see a conditioning bar, but this is the parameter, right? Not the input. Okay, so this is an unconditional density model. And what do we use the unconditional density model for? To fit some distribution. That is the case of unsupervised learning. Okay, so we can use it in unsupervised clustering. So unsupervised clustering of real valued data samples. Unsupervised clustering of real value data samples. So that is yn being d-dimensional. Okay, and how do we do this process? So how do we fit this joint density? I am telling about this P of y given theta and you learn it, but what do we mean by learning it? That is the important question, right? So how do we do the process? So to learn, how do we do the process? The first thing is we have to fit the model. All right, so we fit the model, and by fitting the model, what do I mean? We find the theta hat that maximizes the log likelihood, right? Lecture 1. Okay, so we do it by maximum likelihood estimation and find out the parameter theta hat, okay, that maximizes the log likelihood, log P of d given theta. All right, and the data d of course has 1 to capital N samples, and then that is the first step. So here we are doing unsupervised clustering. Means what? That let us say you have some set of data points, right? And you want to group them into some kind of clusters. Let's say this is a blue cluster, okay? And then let's say you have some another cluster like this, okay, and then you can have other clusters as well. For instance, you may have um, another cluster, and you can have some another cluster, okay. So you can have a lot of clusters. So how do we do this unsupervised clustering, right? So that process, and when we study clustering in details, we will learn about the process, but here I'm giving you the intuition. And then the next part is, see, each data point is coming from some cluster, right? Let's say here k is equal to 4, but we can have any number. That also is a hyperparameter, okay? So we associate each data point, okay, which is my yn, with zn, or the cluster it was generated from, used to generate yn, okay. And we do not know this z of n, right? So we can always assume some prior, we can assume some prior on the latent, we can take a Gaussian prior, okay, or any prior depending on the input, and then we can revise our beliefs by using Bayes rule to compute the posterior. So we have to compute something called as responsibility. The posterior is the responsibility of the cluster k of generating the data point n. That is what I'm saying. I'm saying what is the responsibility of the cluster k for generating the data point yn, right? So we have Rnk is the responsibility, which we can write it as P of Zn equal to k given yn comma theta. So we compute a posterior, right? Meaning that given my data point yn, what is my revised belief of it being generated by the kth cluster? Zn is generated by the kth cluster. All right. So how I can do that? And of course, this Zn can take values between 1 and capital K, because we only have capital K clusters, right? So how we can do that? We can use the Bayes rule to compute the posterior. All right. So we can use the Bayes rule. So P of Zn equal to K given theta. So prior times likelihood, okay, divided by the marginal. And what is marginal? It's marginalized over. So P of yn given Zn equal to K prime comma theta into P of Zn equal to K prime given theta. All right. And then how do I choose? So Zn hat, if I have to choose the specific cluster, how will I make the choice? So I take the, so I should select argmax k, meaning what? I want to know which cluster was generated by the data point n, or which cluster generated data point n. So for that I have to find that case which has the maximum posterior, because let's say for cluster 3 it was the highest. That means cluster 3 was most involved in generating the data point yn. So if I have to associate that point with its, let's say, specific cluster, then in that case we take argmax. And see, this is hard clustering, because we are saying that y3, let's say, was generated from cluster 2, but we can also have the case that, let's say, y3 was generated from 50% of cluster 2, 30% of cluster 1, right? That is called as a soft assignment. Here we are doing as hard clustering. Argmax means it is hard clustering, okay? So what we have is argmax of k, r and k, and it's better to take logs, right? Because if I take logs, products become sum, and the bottom is independent of Zn, because we have marginalized it. All right. So argmax of k, all right, log P of Zn equal to k given theta plus log P of yn given Zn equal to k comma theta. All right. So this process is called as hard clustering. This clustering that we are doing here is a hard clustering. Okay, hard clustering. So let me erase this part. All right. So again, let me write down the equation. So Zn hat equal to argmax of k log p of Zn equal to k given theta plus log p of yn given Zn equal to k comma theta. All right. Now, what we discussed there was hard clustering, right? But if we do not choose the argmax, then we have the case of soft clustering. All right. So in the case of soft clustering, I explained soft clustering. I'm just writing down soft clustering. We fractionally assign each data point to different clusters. We fractionally assign each data point to different clusters. Okay, you have heard about the k means or the k neighbors, right? So that is a special case of this, as we'll see. So you see, so if we have a uniform prior over Zn, that is, this term is a uniform distribution, and we use spherical Gaussians. That means the Gaussians that we are considering, each mixture component is a spherical Gaussian. That means in the covariance matrix it has just one free parameter, or it is a diagonal matrix where all the diagonals have the same value. Clear? These things I have covered already. Please check the previous lectures if you have forgotten. We use spherical Gaussians, sigma k equal to identity. Then in that case, this hard clustering problem will reduce to a k-mean problem. The kn in the nearest neighbor, the k mean, basically the k means clustering that we have, right? The k means clustering, sorry, not the k nearest neighbors. K nearest neighbors is the supervised case, right? And k means clustering is the unsupervised. So you should keep these things in mind. These are very confusing terms. So yn minus mu k hat whole square. So we will derive this in when we study clustering, that how this thing comes from here. But see, the point is simple, right? That if I assigned some cluster has some mean component, right, mu k hat, then yn, whichever mean it is closest to, that will be the cluster from which yn was generated. All right. Okay. Next example that we take is of Bernoulli mixture models. And this has a very interesting example, right? For instance, if you want to generate, let's say you want to do some classification of digits, in that case actually you can use a Bernoulli mixture model if you want to do classification in an unsupervised way. So let me tell you what I am trying to do. And basically what happens is that you see that you have an image, right? And images have these bits. So each bit you can model it as a each bit, each dimension, right? Or each dimension. So the images have dimensions. So each dimensions can be modeled as a Bernoulli. And then once you model it, and when you use this Bernoulli mixture model, you will see that when you learn and do this model fitting, the process that I have described here, it will learn some kind of representation of each digit. So it can actually classify digits. All right, that is the interesting thing. Let me erase this part of the board. So Bernoulli mixture models. Okay, so Bernoulli mixture models, what we can do is, okay, so if the data is binary valued, if the data is binary valued, we may use a Bernoulli mixture model or a BMM. All right, so what will be the likelihood equation? So it has capital D dimensions, and we are having the independence assumption that each dimension is independent of the other dimension. All right, so in that case, what do we get? Bernoulli of yd given mu dk, because each bit yd is generated from a mean parameter mu d, but that dimension is coming from some kth mixture component, right? This is small k, so mu dk. Okay, so how I can write down the equation? Capital D, all right, mu dk to the power yd into 1 minus mu dk to the power 1 minus yd. All right, where mu dk is the probability that bit d turns on in cluster k, turns on in cluster k. All right, and generally we take, for the MNIST case, if I take k as 20, then you will see that the model will discover a representation for each digit. Okay, so model discovers a representation for each digit. Okay, that means if you see, this is the image, right? Let's say this is 1, so this will be one mixture component, let's say some k equal to, let's say 1, and it will have some, let's say 0.06 as the prior probability of happening. So in that way it will learn 20 mixture components. Okay, that it is an example. You can check out GitHub, and codes are also available, but I just wanted you to give this concept that the Gaussian mixture models can be so expressive. All right, next topic is probabilistic graphical models. So probabilistic graphical models. So we need probabilistic graphical models. Why? Because when we have complex systems, okay, and we want to treat those complex systems in simple ways, then we have to represent them as graphs, as directed acyclic graphs, and make some assumptions called as the conditional independence assumption. I discussed with you conditional independence, right? For instance, think about a structure. Let us say that we have this kind of structure where, let's say, the sky is cloudy. Now a cloudy sky can lead to rain, right? And a cloudy sky can lead to the sprinkler, the water sprinkler that we shower on the ground. How? If the sky is not cloudy and I want to give water to my grass, I need to turn on the sprinkler, right? So we can have two arcs. From cloudy, cloudy can cause rain, and cloudy can cause sprinkler to turn on. But think about another, so what are these basically? Cloudy, sprinkler, rain, wet grass. So these are the examples of basically some random variables, let's say. So let us say that sky as a cloudy is a random variable. All right. Now, if the sky is cloudy, it can cause rain. All right. And it can also cause some interaction with my sprinkler. How? If the sky is cloudy, I'll not use the sprinkler maybe to, shower my grass. All right. So we can have that. And then in the last part, we have, let's say, wet grass. Now, the thing is that you see, wet grass, I can say, depends on sprinkler and rain, but not on the cloudy. Because if I know that I am using the sprinkler, and if I know that my it's raining, then I can always know whether my grass is wet or not. I do not need to know about cloudy. So there will be no arc in my graph from cloud to the wet grass. So that is a kind of a conditional independence assumption. And this conditional independence assumption is very important because it helps us to simplify our models, right? When we want to write down these joint distributions, we want simple ways of writing them. All right. And when I discuss Markov chains, how we have language models, you see that this conditional independence assumption plays a very important role. Okay. All right. So let me write down the full formal treatment. To treat complicated systems, and this was actually mentioned by a famous scientist, Professor Michael Jordan. Okay, Professor Michael Jordan. And what he mentioned is that to treat complicated systems, we use two ways. One is called as the principle of modularity, and another is called as the principle of abstraction. Now, when you write a joint density, let's say P of y, let's say P of y1 comma y2, right, as P of y1 into P of y2 given y1, right? So you have broken down a joint into a marginal and a conditional, all right? And often, when I use this marginalization thing, sum over the latent hidden variables, we do that, right? So what is that? That is basically abstraction, right? When I'm marginalizing, I am abstracting out that hidden variable, all right? Okay, all right. So let me erase this. So principle of modularity is via factorization. Okay, and abstraction is via averaging. All right. So, and of course, we have conditional independence assumptions. We studied conditional independence, right? And conditional independence are assumptions are very important if we really want to, simplify our calculations. And this is done using graphs. Okay. So when I write this kind of way, P of y1, y2 is equal to P of y1 into P of y2 given y1, I am basically combining multiple blocks, right? The conditional and the marginal into the joint. To yield the joint, okay? All right. So the formal treatment now. A probabilistic graphical model a PGM or probabilistic graphical model. A PGM is a joint probability distribution that uses a graph structure to encode conditional independence assumption. Independence assumption. All right. Conditional independence assumption. So we use directed acyclic graph and we call them as Bayesian networks. Okay, although there is nothing inherently Bayesian about such networks, but we call them Bayesian networks. Now let me raise this off. So in our directed acyclic graph, we follow topological order. That is, my graph has nodes as random variables. So if I consider some random variable yi, the topological order means children, parents before children, right? So node yi, and the conditional independence assumption we have is that the node yi is independent of its predecessors, excluding the parents, of course, because we have to condition on the parents. Okay, so that way. So I'll explain with an example, but this is conditional independence. So if I know the parents, if I observe the parents, then of course the children will be independent of what is the predecessor of the parent. All right, because all the parents of the children are sufficient to define the information about the child. Okay, okay, so this is called as the ordered Markov property, because we have ordered that. Okay, parents before children, so that is the ordered Markov property. Ordered Markov property. So the joint, because of this assumption, you see our joint becomes so simpler. P of y1 to all the nodes is just the product. You see, if I did not use this assumption, then by the chain rule of probability, this side would have grown, right? Because P of x1 to xn is what? P of x1, x2 given x1, then x3 given x1 comma x2. So you see the number of variables it is conditioned on is growing exponentially. But if I make this conditional independence assumption, which is fairly reasonable to make if we can construct that specific graph, directed acyclic graph, then you see it gets so simplified. So you see, if we have the domain knowledge about the problem that we are modeling, and if we can construct that PGM, then our solving of that problem can become so simpler, because we can define the joint in such a easy fashion. I give you an example and then show you how it becomes simple. So let's take an example. So let us consider, say that we have random variable. So let's say cloudy. Okay, so the sky can be cloudy. All right. So let's say cloudy sky. We have to assign some probabilities to it. So let us say that I'm giving you an example of a DAG, okay, of a probabilistic graphical model. Now see, cloudy sky can lead to rain, so we can have another random variable. So these nodes are random variables, okay? This thing you should keep in mind. All right. So if it rains, so this is the cloudy sky, okay? So if the cloudy sky is false, or if it is true, on the basis of that, we can have the being the rain's probabilities being defined, right? So of course, if the sky is not cloudy, we are more likely to not have rain, and vice versa. These are just numbers, these are not like something sacrosanct. I'm explaining with an example, so we are using just some numbers, okay? Then cloudy sky can lead to sprinkler as well, because if the sky is cloudy and if I want to water my grass, I will turn off the sprinkler. If it is not cloudy, I'll turn on the sprinkler. All right, simple as that. So again, you can have some C, you can again have some kind of this for this as well, okay? So C can be false or true, and on the basis of that you can have your tables. All right, you can have uh, sprinkler taking false or sprinkler taking true. And see, this is the interesting part. Now whether it rains or the sprinkler is on, these two are sufficient for me to define whether the grass will be wet or not, right? See, cloudy sky has no relation with wet grass, okay? This has no relation. So this has no relation, because the relation is mediated by these parents of the child wet grass, okay? So you see, for the wet grass, if I construct, so the sprinkler and the rain will be the parents, all right? And wet grass can be false or wet grass can be true. This can take like various values, all right? And this will be a 4 by 2 table, because each parent can take two possible values. They are binary, so it will be product of 2 into 2, that is 4. All right, so you can have different cases, right? And logically you can give values to these as well, so I'm not taking time giving them. So see, the interesting part is, what benefit do I get by making this PGM? Okay, so what's the benefit? That is the bigger question, right? What's the benefit? Of course, I should have some benefit because I've got some domain knowledge, right? Because if I would have no domain knowledge, wet grass would depend on cloudy. But now you see, when I write down the joint equation, it gets so simpler, all right? And that is the beauty of probabilistic graphical models. So if I write down the joint, let's say this is C, S, R, and W. So P of C, S, R, W is equal to what? If I write down logically by the chain rule, P of S given C into P of R given C comma S into P of W given RCS. Now see, these terms can be so big, right? If you look here closely, this table size can grow so big, because see, when it is depending on 2, already there are 4 rows, right? So you see, these tables will keep on growing. But the beauty of conditional independence assumption is that By conditional independence assumption, which I used over here, that the child is independent of its predecessors, conditioned on its parents, and it makes total sense, because if I know if it rains or not and the sprinkler is on or not, then I can always infer whether the grass is wet or not probabilistically. I do not need to know about whether the sky is cloudy or not. Okay, so what do I get? So I can, what I can do, so R is C, I can stuck down this S, because sprinkler and rain have no relation. Okay, and I can also stuck down this R, this C. So the equation C simplifies to P of S given C, P of R given C into P of W given R comma S. This is simpler than this one, right? So that is by conditional independence assumption. So some terms and terminologies. Okay, so this term P of yi given ypa of I is called as the conditional probability distribution, or the CPD. Okay, conditional probability distribution. Distribution for node I. And looking at these things, what are they? They are tables, right? You see, categorical tables, right? So this is each CPD is a categorical distribution. All right. So each CPD is a categorical distribution. Okay. Now, when I'm defining the parameters, I define it like this. Theta ijk is probability that yi is equal to k given y parent of I equal to j. And I will explain it, like what it actually means. Ki theta ijk equal to 1, and theta ijk is between 0 and 1. So what do I mean by this term? See, probability that node I, let's say wet grass, takes on some k, state k, that is, let's say this is the kth, right? So it can take state false or state true, condition on the parent of I becoming j. So j is the row, right? For instance, take for this case, for the rain case, the parent is the cloudy. So parent of I takes state j, that is, this is the jth, this index is j index is row. All right. And this is the node, rain is my current node, yi equal to k. So you see, if I sum along the ki's, that is along this, the sum should be 1, 0.8 plus 0.2, and that is what probability distribution means, because it has to sum to 1, right? So I is basically my node. So, and small k is the node states, the states my node I can take. Okay, so ki, and j indexes the parent, the joint parent states, right? See, here I have 4 states because there are 2 parents. Okay, and likewise, so j indexes the joint parent states. So how many states I can have? Ji equal to, so I take all possible parents of my node I multiplied by the cardinality of the parent, that is how many states it can take. For instance, here it has 2 parents, each parent can take 2 states, so the joint parent states is 4, so 4 rows. All right. Okay. Now we discuss the Markov chain example. Okay, Markov chains and that stuff. So Markov chain, the name it itself means that we have a chain kind of a graph structure, right? It's a chain, and we have we have some Markov assumptions. That is some conditional independence assumptions. Okay, so we create a joint probability distribution over variable length sequence. That is, let's say, from 1 to capital T is my sequence length. So I want to create some joint probability distribution over variable length sequence. So you see, each variable of my sequence, let's say if it's a sentence, so each variable is, let's say, a word in that case, right? And each variable represents, so let us call that as y small t, because I've used y here, represents a word from some vocabulary. So y small t is a categorical distribution, right? So yt can take values from 1 to capital K. Then the resulting model that I get, model is basically a distribution over possible sentences. Okay, so distribution over possible sentences of length capital T. Length capital T. All right. Okay. This entire thing, this thing is what, they call it as the language model, because you have some sentence, a sentence, and each word from the sentence is drawn from some is a word drawn from some vocabulary. So it's a categorical distribution. So we have a distribution over a categorical distribution. That is a language model, and you can model that as a Dirichlet distribution, which I have not covered, but for now this idea is sufficient. Okay, so using the chain rule of probability, now why do I need Markov chain? Because we will come to this chain rule of probability and then we simplify it using conditional independence assumptions. Okay, that's the utility. So using the chain rule of probability, what do I get? So P of y1 into P of y2 given y1. You see, as I go beyond, then the size of the categorical distribution increases exponentially, right? It is 2 here, it will become 4, and then it will become 2 to the power t minus 1. All right. So this is very large, right? The number of parameters grows exponentially. And this is not feasible to represent, right? Because the number of parameters to represent these categorical distributions, these categorical distributions, okay, grows exponentially. All right. That is why we need to make conditional independence assumptions. So we need to make conditional independence assumptions. And that assumption is that if I consider, let's say I am at the tth word, okay, so conditioned on my tth word, okay, the sequence starting from t plus 1 will be independent of the sequence before tth. So what does that mean? It means something like this, that let us say these are my random variables and I have a chain. All right, let's say I have a chain and this goes on. So let us say that if I condition on y3, then conditioned on y3, y4 to t will be independent of y1 to 2. So if I condition on y3, these two are like independent of each other, because observing y3 will tell me about y4. All right, I don't need to know information about y2 and y1. So this is the first order Markov assumption. That means what? Conditioned on y3, I can find the distribution of y4. Okay, if I condition on y3, I do not need to take into consideration y1 and y2. All right. That means what? This joint will then become what? This joint will become simply, this part will become, so see, first I have p of y1, then y2 is conditioned on y1, right? If I condition on y1, I have this category. Now for p of y3, if I write this, of course I don't need y1. Why? Because if I observe y2, I can write down the distribution y3 given y2, because if I observe y2, I do not need to know about y1, right? So you see how simpler this has become from this, okay? Yt minus 1. All right. You can write it as, so p of y1 into product t is equal to 2 to capital T, p of yt given yt minus 1. Okay. So this beautiful equation is called as the first order Markov chain. Okay. First order Markov chain. This is the first order Markov chain. So what will second order Markov chain be? In that case, let's say yt will depend on yt minus 1 and yt minus 2. That is second order. Okay. So before I come to that, let us write some of these things as well. So you see, now these things that I am writing, okay, this p of yt given yt minus 1, this distribution, probability distribution of the y small th sequence conditioned on yt minus 1, this is some kind of distribution, right? So we call it as the transition function. Why transition? Because it's describing how we are transitioning from yt minus 1 to yt. All right. Okay. So this is the transition function or the kernel function. Okay. So p of yt given yt minus 1, this is more than 0. Okay. And of course, by the definitions of probability, p of yt equal to, let's say this is some small k and this is capital K, all right? So this thing given yt minus 1 equal to j should be 1, okay? Why? Because it's a distribution, right? So it should sum to 1. This thing summed over all values should be 1. And if I construct the matrix, because you have j and you have capital K terms, right? Like you can have k by k. So this will be a matrix. You can have a matrix, a stochastic matrix of the transition. So this describes the transition from state t minus 1 to some state t, right? And so t minus 1 can take capital K values, state t can take capital values. So we have k by k possible transitions, right? So it's a k by k matrix, as simple as that, okay? So, and what will be the element of that matrix? The jth row and the kth column will be P of yt is equal to k given yt minus 1 equal to j. All right. This is called as the state transition matrix. And you see that here we are considering evolution of time steps, right? So if this matrix, if the stochastic matrix is same for all time steps, that is, it is not changing, then we call it as a homogeneous, stationary, or time invariant model, okay? So it is said to be homogeneous, stationary, or time invariant matrix. All right. This is also called as parameter tying, meaning that across the time steps, the parameters are same because the matrix is same. The parameters are shared. Okay. So we can model arbitrary number of variables using fixed number of parameters because of parameter tying. So we can model arbitrary number of variables, and this is good, right? We can only need now fixed number of parameters to model arbitrary number of variables. With increase in variables, our parameters does not need to increase. So computationally very efficient, right? With respect to memory space as well. So we can model arbitrary number of variables using fixed number of parameters. Okay. Now let me erase this part. So first order Markov model was this one. So what will be mth order Markov model? Mth order Markov model will be so 1 to capital T, okay, and so first 1 to m will be there, and then from m plus 1 to capital T, so it will depend on the last m terms, right? So that is why t minus m to t minus 1, it will depend on the last m terms. So if m is equal to 2, you have heard about this, right? So here m was 1. So this is called as the bigram language model. That is, you are modeling over word pairs. Okay, bigram language model. So modeling over word pairs. Okay, and if m is equal to 2, it is a trigram language model. It's a trigram language model, that is, we model over word triples. So y of t depends on yt minus 1 and yt minus 2. All right. Now there's another point, is that if I want to draw for trigram, how will the structure look like? So see, y1, y2 we can't help, it only needs y1, but for y3 it will need y1 and y2, right? y4 will need y3 and y2. So this is the graph DAG for the trigram language model. Okay. Another interesting point to note is that if the vocabulary is large, then the number of parameters can actually be very large. Okay, in that case we assume that this this p of yt given yt minus 1 yt minus 2 or something, it basically we do a rank decomposition of this distribution. All right, what I'm trying to say is that if vocabulary is large, the number of parameters becomes very large, because you know that if it's a 40,000 vocabulary, then even categorical distribution over word triplets can be what, 40,000 squared, right? It can be so big, because each variable can take 40,000 states, and for each you have another 40,000 states, right? So that is why, so we need to make assumptions beyond conditional independence. Okay, so we need to make assumptions beyond conditional independence, and because of that we use a neural language model. Okay, and what is this neural language model does? This neural language model actually, what it does is that it represents this thing as a low rank matrix, right? So neural language model, what it does is that this distribution, it represents as a low rank matrix. So if it is a low rank matrix, if I can do some rank decomposition, let's say using singular value decomposition, that we will study when we study linear algebra, in that case this can be very simpler. Okay, all right. Next part is the inference part. Okay, we are left with inference, and then we study learning, and then the plate notation, and then we are done. So inference, so we have the following case, that we have the inference means what, we are like computing the posteriors and stuff, right? So the probabilistic graphical model is a joint probability distribution, right? And what we did was we used marginalization and conditioning to compute the posterior. So posteriors were computed using marginals and conditionals. The Bayes equation that you remember. Okay. And for instance, let's say I know that the probability that the rain happens is, let's say, 1 is, let's say, 0.5. But let's say if now somebody told me that the grass is wet, then the grass can be wet maybe because it has rained, right? So I will more likely to infer that it has rained. So this is like an inference that we have made, right? And this probability will be more, because if I know the grass is wet, of course it could be due to sprinkler, but it can also be due to rain. So the chances of rain have increased, right? Logically speaking. And so we are taking that example, that PGM that I drew, right? But now think this way. Let's say that in addition to wet grass, I am also told that the sprinkler was on. Then in that case, what is the probability that it has rained? So this will be lesser than this one, right? Why? Because now I am told that the sprinkler was on. So probably the grass is wet because the sprinkler is on, right? So it means that the fact that it rained should be now low probability, because I'm making some inference based on what I'm given. If the sprinkler was already on, then of course wet grass also remaining on means that it is not that likely that it rained. If we consider that specific case when the grass was wet and the sprinkler was not, no information about the sprinkler was given. Okay, so this interaction, this interaction that we have, this interaction, that if I get more information of, let's say, sprinkler, the probability of rain has reduced. This is called as the basically this Bergson's paradox, where you have, let's say, two causes of something. Let's say wet grass has two causes, or let's say rain has two causes, wet grass and sprinkler, right? So if one cause is known and if the other cause is known, it can change our beliefs. Okay, so this is called as the, or you can write it as the explaining away effect. Get the idea. Okay, don't memorize these terms, Bergson's paradox. No, just get the intuition, get the idea. That is more important. This is called as the Bergson's paradox. Bergson's paradox. Next part is learning. So if the parameters so each node in our probabilistic graphical model is represented by a categorical distribution, right? Now the random variables are, of course, the nodes are random variables. But what about the parameters? We want to estimate the parameters, right? And to estimate the parameters, to infer the parameters, I have to do something. So that comes under the learning category. So if the parameters are unknown, we can add those parameters as nodes to our graphical model, which I will explain with one example of Gaussian mixture model, right? So because we want to estimate the parameters, so we add those parameters as nodes to our graphs, and then we estimate them using inference techniques. Okay. So if parameters of CPDs are unknown, we can view them as additional random variables random variables okay, so as hidden variables to be inferred. So if the parameters of CPDs are not known, we can view them as additional hidden random variables, okay, to be inferred. How? I will explain it with an example. Okay, so let us say that I have, let's say, um, a theta as my parameter, let's say. Okay, so this is the node for the theta parameter, and let's say I have observed y1 to yn independent random variables. So you see, conditioned on theta, all of these are independent, all right? So yn are conditionally independent given theta. Okay, so here what the setup is that we have n independent and identically distributed random variables drawn from the same distribution. Okay, and it has a common parameter theta. So theta as common parameter. Okay, so basically instead of writing y1 to yn copies, we use something called as the plate notation. And in plate notation, so you see here I have shaded that, right? The shaded quantities are the observed and the unshaded ones are to be estimated. Okay, so get this idea clear. So unshaded are the hidden quantities to be estimated and shaded are the observed. Okay, so we don't need to write it as n copies, we can just make a plate diagram. So from theta, okay, I observe yn independent samples, and of course we have the plate notation. This is the plate notation. Okay, capital N copies. Now what is the generative story for this? When I want to make inference, the generative story, so I have theta, which is my unknown hidden parameter. So we treat it as a random variable, right? So since we do not know, we can give it some prior, right? So theta is sampled from some prior distribution. Okay, so this y of n sampled from p of y given theta is my specified likelihood. Okay, so this quantity p of theta into p of d given theta, right? So this is p of theta into product small n equal to 1 to capital N p of yn given theta. Here we make the IID assumption. Okay, now for a Gaussian mixture model, if you recall, for a Gaussian mixture model, what will be the plate diagram? We studied Gaussian mixture model, right? So the latent is there and the prior on the latent is unknown, right? So we can treat the prior on the latent as a hidden random variable to be estimated, right? So from the latent we get from the prior we get the latent, and using the help of latent and taking for each latent we have capital K such latents, right? So for each latent we will have its mean and its covariance, right? Each latent has its mean and covariance, right? So that is also to be estimated, and using that using the latent. And so first I sample the latent mixture component, and then it's given that latent. I mean, I do not sample it, I sample the observations, but observations are sampled from what? From some latent, right? And given that mixture component, we consider that distribution, so we have to consider its mean and covariance, and on the basis of that we get a sample, right? And how many samples we are taking? Capital N. So we only know this yn because that is the only thing observed. These unobserved quantities, mu k, sigma k, pi, we treat them as random variables to be estimated. So you see here, mu k and sigma k, there are capital K copies of it, right? For each small k, we have the copies, right? And for Zn, we have capital N copies of that. We have 1 to capital N times. So we do not write it, we just give a plate notation. Plate notation means what? You see, here when I'm taking capital N observations, I don't have to write it like this. I'm just using a systematic notation, which is called as the plate notation. Okay, so if I have to write down the density equation, how will I write it down as? What will be the density equation if I have to write it? So very simple. So this is a Gaussian mixture model as a probabilistic, as a graphical model, all right? And what will be the equations of it? So if I have to write down this equation, so P of, I'm talking about this one, and Z1 to capital N, the joint density. So first we have to write the density of the prior, P of pi, okay? Then how many mixture components we have? Capital K, and each mixture component has its mean and covariance, so we need to write down the probabilities for that. And then we have the what? The conditional, this yn thing. So how can I write it? I can write it like this. I have capital N samples, all right? And how do I write it? So see, first I get the latent from the prior, and then from the latent, okay, from the latent, and from the latents, from its mean and covariance, we get the observation, right? Because observation is coming from what? The mean and covariance, okay? So mu 1 to k, sigma 1 to k, P of yn. So that is what the equation becomes. So let me write it a bit nicely. P of y1 to n, z1 to n is P of pi, okay, product densities for this, because these are not observed, right? We have to estimate this, so this will also come under the prior. And then since we have IID assumption, so this will become product, okay, into P of yn given Zn mu 1 to k comma sigma 1 to k, all right? Okay, and what are the parameters? So the parameters are basically, in this case, the parameters are pi and mu, okay? So with this, we cover our multivariate module for the probability. From next class, we start with statistics. Thank you.